Hello students, I am Dr. S.M. Bhatti. The objective of this video is to find Fourier transforms of different type of functions. In my last video, we have solved 4 examples where we obtain the Fourier transforms of the given functions. Today is the example 5 here. Find Fourier cosine transform of e raised to minus mx, where m is a positive number, x is a positive number, positive real numbers. Hence, prove this integral is equal to pi upon 2 e raised to minus mx. Given function is e raised to minus mx, so we take it as a f of x, and by replacing x by u, we can have f of u is equal to e raised to minus mu. Note that here x and m both are positive real numbers. Hence, u also became positive real number. Fourier cosine transform of the given function f of x is capital epsilon lambda, and it is given by this formula. This is equation number 2a, where we have to put the value of f of u. You can see above, f of u is e raised to minus mu, so you can put that value here. Now look at this right hand side. In right hand side there is an integral, and you can see that the right hand side is the integral of the type integration from alpha to beta e raised to au cos bu d. Hence we have to use this formula, right? Integration from alpha to beta e raised to au cos bu du is equal to e raised to au upon a square plus b square into a cos bu plus b sin bu, and limits are from u equal to alpha to u equal to beta. Now if we compare this right side with this left side, easily we can get the value of alpha. Alpha became, here alpha is lower limit, here lower limit is 0, so alpha is 0. Beta is your upper limit, here upper limit is infinity, so beta is infinity. Here a became minus m and b became lambda. Please note that here u is a variable of integration and lambda is here cost. So simply you apply formula, you can find the next step. We'll see that in next page. So applying above formula, we can get this kind of right hand side. Okay, then we put first u is infinity. When we put u is infinity, what you find here in numerator, e raised to minus a positive number into infinity. That became e raised to minus infinity, and we know that e raised to minus infinity is 0. That means when we put u as an infinity, this expression became 0. Then there is a minus sign, and now we have to put u is 0. So when you put u is 0, e raised to minus m into 0, that is e raised to minus 0, that became 1 upon m square plus lambda square as it is, and further you will find minus m cos 0 plus lambda sin 0. Now you know cos 0 is 1, sin 0 is 0, so you will find in the bracket minus m plus 0. And when you simplify this, you can get the epsilon lambda, and that epsilon lambda is m upon m square plus lambda square. In this way, we obtain the value of epsilon lambda. We can call this equation as a 1. Now, the inverse cosine transform of epsilon lambda is given by this formula, and this is your equation 2b. fx is equal to 2 upon pi in integration from 0 to infinity epsilon lambda cos lambda x d lambda. This is nothing but equation number 2b, which gives you value of f of x, that is inverse Fourier cosine transform. Now here we will substitute the value of epsilon lambda, which we just obtained above. Means put the value of epsilon lambda as m upon m square plus lambda square, we can get this kind of step. And you will find that if you take this 2 upon pi in the left hand side, without disturbing this integral, if you take 2 upon pi on the left hand side, we can get the value of this integral as pi upon 2 e raised to minus mx. So in this problem, we have obtained Fourier cosine transform, and we have used this Fourier cosine transform to evaluate this kind of integral. So in this way, we have seen the one application of the Fourier cosine transform. Once you obtain Fourier cosine transform, using inverse transform formula, we can obtain the value of certain integral. In the previous examples, we have obtained only Fourier transform or Fourier cosine transform, Fourier sine transform, straightforward way. But here in this example, we have used our cosine transform to evaluate some type of integral. Now we'll take the next example where we have to find this kind of a transform. Here is the sixth example now, where we have to find Fourier transform of the function f of x. And this function f of x has two values. One value is 1, another is 0. Now when it has value 1, when mod x is less than or equal to 1, and it has a value 0 when mod x is greater than 1. Hence evaluate integral from 0 to infinity sin x upon x dx. Now first you have to understand what we mean by mod x is less than or equal to 1. Note that mod x is less than or equal to 1 means minus 1 less than or equal to x less than or equal to 1. And another interval we have mod x greater than 1 means x is between minus infinity to minus 1, that is minus infinity less than x less than or equal to minus 1, and 1 less than or equal to x less than infinity. I can show it in terms of the figure also here. Suppose this is the portion. Here 0 is midpoint. Fine. Here is there is a minus 1 and this is a 1. So this represents the interval mod x is less than or equal to 1. Fine. Now we have to understand the remaining part, that is mod x is greater than 1. So I can show that part also here. For that purpose I will change this okay, I will take red. Fine. So remaining part means I can extend this 1 and I can go up to infinity. So 1 to infinity, and on this side also I can start with minus 1 and I can go to the minus infinity. So this is from minus infinity to minus 1. So mod x is greater than 1 means this kind of portion from minus infinity to minus 1 and from 1 to infinity. Now here 1 is not included while 1 is included in this interval. Fine. Now we can write this function f of x again. So function fx, now it has three intervals. First interval is, you can see, from minus infinity to minus 1. So we write first interval from minus infinity to minus 1. Then second interval is from minus 1 to 0. Sorry, minus 1 to plus 1. So second interval is from minus 1 to plus 1. And finally, we have third interval, that is from 1 to infinity. That is 1 less than or equal to x, strictly less than infinity. Fine. And in the first interval the value is 0, in second interval value is 1, and in third interval the value is 0. This is for the function f of x. Fine. Now this function f of x can also be written as f of u just by replacing x by u. So in this definition, if you replace x by u, you can have this here x, we have x here, we have replaced x by u here. That's it. So in short, function has three values. So in red portion the value is 0, while in this blue portion the value is 1. When u is between from minus infinity to minus 1, value is 0. When u is between 1 to infinity, value is 0. That is in red portion. When u belongs to red portion, the value is 0. When u belongs to this blue portion, that is from -1 to 1, the value of the function became 1. Another important observation is that function fx is an even function. If you apply definition here, because function is defined in the interval of the type -L to +L, and you will find that f of minus x is equal to f of x. Hence, we can say that function is even. So we can use the property. And this kind of property already we have used in the previous lectures also. Capital F lambda is equal to 2 times fc lambda. So this is a very important property. If function f of x is an even function, then capital F lambda is equal to 2 times Fourier cosine transform, that is 2 times fc lambda. And but you know definition of fc lambda, it is integration from 0 to infinity fu cos lambda u du. This happened by equation 2a, and now we have to put the value of f of u. But as you have seen that if you consider interval 0 to infinity, the function has two values. One is 0, another is 1. So accordingly you have to split, right? So if you observe the interval 0 to infinity, right? So we have to split this interval in 0 to 1, then 1 to infinity. So same integral we have written as sum of two integral with limits 0 to 1 and then 1 to infinity. The integral remains same. Now in the interval 0 to 1, the f of u has a value 1. We have seen that in the previous page. And here is a in the interval 1 to infinity, f of u has a value 0. So 0 into cos became 0, and integration of 0, if limits are present, it became 0. Fine. And here f of u is 1 in the interval 0 to 1. 1 into cos lambda u became cos lambda u, and integration of cos lambda u with respect to u became sin lambda u upon lambda. Note that here lambda is a constant, and here limits are u equals 0 to u equal 1. Now we put u is 1, you can find this first term. Then you put u is 0, you will find second term, and between them there is a minus sign. You know sign of 0 is 0, so second term became 0 here, and in this way we obtain Fourier transform. We obtain the value of capital F lambda as a 2 sin lambda upon lambda. Now by inverse Fourier transform of capital F lambda, fx is given by 1 upon 2 pi integration from minus infinity to plus infinity capital F lambda e raised to minus I lambda x dx, right? And okay, here is actually so here note that e has a power plus I lambda x d lambda. So here is the power of e is plus. Here we put the value of capital F lambda as a 2 sin lambda upon lambda. In next step 2 will get cancelled, and we can have this equation. And remember, we have to evaluate integral, and in that integral we don't have this exponential term, so we put here x is 0. We will not disturb lambda because lambda is variable of integration, so we put here x is 0. So put x is 0 in both sides. Left hand side became f of 0, right hand side e raised to 0, and you know e raised to 0 here, it became 1. So next step you can get now. Next step became 1 because f of 0 is 1. If you look at the definition, you'll understand that 0 is between -1 and +1, and in the interval -1 to +1, the function has a value 1. So and 0 is between -1 and +1. So f of 1 became 0, and hence left hand side, sorry, f of 0 became 1. So left hand side became 1, right hand side as it is, right? Then you take the pi in the another side, we can have an integral from minus infinity to plus infinity sin lambda upon lambda d lambda is pi. Now sin lambda upon lambda is a even function. Sin lambda upon lambda is an even function, and here so using the property, this integral is nothing but 2 into integral from 0 to infinity sine lambda upon lambda d lambda. This 2 can be taken in the right side. It became now pi upon 2, and here in left hand side we have lambda as a variable of integration. But you know, in definite integral variables are immaterial, so we can change lambda by x, or simply if you put lambda is x, you can have this, and in this way we have obtained the value of integral from 0 to infinity sin x upon x dx is pi upon 2. So to make this video, I have used two references. One is B.S. Gravel, Higher Engineering Mathematics, Kanna Publisher, and second is a book, a textbook from S.R. Sakre, B.S. Wage, myself, S.M. Bhatti, Nivin Mani. Thank you very much for watching this video completely.